All right, it's 2:30, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? It seems like everyone's tired and ready for summer, right?
I'm always that way.
we got 2 more weeks to go. So we got today, we got next week, and then finals, and then that's it. So almost at the finish line, guys. So you're almost there. Okay. And so today the plan is we're going to be continuing on with radiation exchange. Okay. And so today, you'll start to see some problems that are actually a little bit more practical than the ones we've been doing because up to this point we've been covering. I would say I would kind of consider like kind of the background knowledge, background concepts behind radiation. Today you'll actually see that used to actually compute some heat transfer. And so this will be hopefully a better lecture than the last, because I know the last few have been a little bit dry. Okay. And so so far we're still on schedule, and so my plan for the rest of the class is for today and for next week is to finish up all the radiation stuff by Monday, and then next Wednesday we'll just have a review session for the final. Okay. And so I wanted to have the final review session kind of in person so that you guys can have a chance to ask questions and interact, rather than just having a pre-recorded thing. All right. So are there any questions I can answer before we get started? Okay. All right. And so we're in the middle of talking about radiation exchange. Okay. Right. And what this is this is basically the exchange of heat between two different surfaces via radiation. Right. And so if you have two surfaces, so let's say that we have one surface like this, maybe another surface like this, okay? We know that since both of these have a non-zero temperature, they're going to be radiating heat, okay? And they're going to be radiating heat on each other, okay? Right? And so there's going to be an exchange of heat going on, right? And so what we defined last time was that this QEX, or this exchange of heat between the two surfaces, is defined by, we'll call this surface 1, we'll call this one surface 2, okay? Right. Right. And so one way that we can define this radiation exchange is we can say it's equal to F12 times A1 times sigma times the difference between T1 to the fourth minus T2 to the fourth, okay? Right. Or what we can say is that this is equal to F21 A2 sigma times the same quantity, okay? Where the key quantity here is these F values, okay? And so these F values here, we define these as the view factors. Right? And remember, the view factors are a number that describes how much of the radiation from one surface hits a different one. Okay. Okay. Right. Because we know that if you have a surface, this can be radiating heat in all directions. Okay. And so the fraction of those radiation waves that actually hits another surface, that's given by your view factors. Okay. And the way that you compute the view factors is, first thing you should try so you can try to see if you can find some either by inspection or to use a table. Okay. And so we'll do an example of that today. And then once you have one of the view factors, you can find all the other ones using the view factor rules, right? So last time we went over two rules. We went over the reciprocity rule or the reciprocal rule, and then the summation rule. Okay. And so this next example will kind of show all of this done in practice for a couple of black bodies. Okay. All right. So this was just kind of a recap from last time. So are there any questions on this before we jump into an example? Okay. All right. So let's do an example and let's see how this is done in practice. All right. And so let's say that we have a rectangular furnace. Right. So it looks something like this. And so we're going to have three different surfaces here. Right. And so we'll call this surface 1. We'll call this surface 2. We'll call this surface 3. Okay. Each of these different surfaces have a length. Right. So let's say that the length of surface 1 here, which is going to be this this dimension, this is going to be 0.5 meters. Okay. And the temperature of surface 1, T1, we'll say that this is 1000 Kelvin. Okay. Right. And so the length of surface 2, we'll say this is much shorter. So we'll say this is 0.1 meters. And then we'll say the temperature of surface 2 is going to be 800 Kelvin. Right. Right. And so the length of surface 3 is going to be the same as surface 1. And so it's going to be half a meter. And then T3, we'll say it's 600 Kelvin. Okay. Right. So those are the three surfaces of our furnace. And so let's say that we also, up here, we have basically ambient air conditions. Okay. And so the length of this opening right here is also 0.1 meters. Okay. And then the outlet temperature up here, T infinity, we'll say is 300 Kelvin. Okay. So that's just about room temperature. Right. All right. And so in this problem, what we want to do is we want to compute the radiation exchange between the different surfaces. In particular, we want to compute the radiation exchange between surfaces 1 and 2. Right. Next, we're going to do surfaces 1 and 3. Right. And then finally, we'll do the radiation exchange between surface 1 and the surroundings. And so in order to do this problem, we're going to need to compute the view factors between each of these different surfaces, which we will be able to find in the book. And then we'll be able to find that in table 13.1. Okay. All right. So any questions on this so far? All right. And so let's go ahead and start solving the problem. And so let's start with surfaces 1 and 2. Okay. So let me go and highlight these surfaces here. Right. And so surface 1 is this one here on the right. Okay. And surface 2 is the one that's below it. Okay. And so, just by looking at this, it's a bit difficult to say, what the view factor is. And so we're not able to solve this by inspection because it's, it's a little bit complicated. And so we're going to have to look these guys up in table 13.1. Okay. And so if you look at 13.1, this looks very similar to kind of our shape factors when we are looking at 2D conduction, right? And so basically, if you look at 13.1, table 13.1, it has lots of different geometries with figures that it shows you, what how you can compute the shape factors for this. Okay, and so for this particular case, between surfaces 1 and 2, this is characterized as perpendicular plates with a common edge. Right? And so the figure looks something like this. Okay. And so you can see here, this is exactly what we have between surfaces 1 and 2, because they are perpendicular to each other. Okay. Or in other words, the angle between them is 90 degrees, and they share a common edge, which is this one right here. Okay. All right. And so if you look in that table, you can see that the formula for the shape factor F12 is given by 1 plus L2 divided by L1 minus. Actually, let me write it down here. A bit more space. Right. So F12 is equal to 1 plus L2 divided by L1 minus 1 plus L2 divided by L1 quantity to the 1/2 power. And so we're going to take the square root of that. Okay. Oh, sorry, there should be a squared here on the L2 over L1 inside that parentheses. Okay. And then we're going to divide all of that by 2. Okay. All right. Right, and so that's the formula from the book. Let me clean this up a little bit here. Right, so L2 divided by L1 quantity squared. Okay, and so if we plug in for L1 and L2, and so from the problem we know that L1 is equal to 1/2 meter, 0.5 meters, and L2 is 0.1 meters. Okay, and so we plug those in, and what we get is F12 is equal to 0.09. Okay. All right. And so from that, we're now able to compute the radiation heat exchange between 1 and 2. Okay. All right. Because from our earlier formula, we know that the radiation heat exchange between 1 and 2 is F12 A1 times sigma T1 to the 4th minus T2 to the 4th. Okay. Right. And so in order to compute the area, we need to compute the width into the page. Okay. Which was supposed to be given to you in the problem, but I kind of missed it. Right? And so the width of those plates into the page is going to be 1 meter. Okay. And so the area of surface 1 is equal to the length of surface 1 times the width. And so this is 0.5 meters times 1 meter. And so this is 0.5 meters squared. Okay. All right. And so we can go ahead and plug in for this Q12. And so first we have F12, which is 0.09. Okay, that's the view factor that we just computed. Then we have A1, which is 0.5 meters squared, which is the area of surface 1. Okay. Then we have the Boltzmann constant. And so the Stefan-Boltzmann constant is 5.67 times 10 to the minus 8 watts per meter square times Kelvin to the 4th. Okay. And then to this, we're going to multiply the temperatures. And so T1 here is 1,000 Kelvin raised to the 4th power. And then we're going to subtract T2, which is 800 Kelvin raised to the 4th power. Okay. And so we plug all that in, and then we do the arithmetic, and we end up with 1506 watts. Okay. All right. Any questions on this part here? Okay. All right, and so that's the heat exchange between 1 and 2, okay? Now let's do the heat exchange, the radiation heat exchange between surfaces 1 and 3. Okay. So just to kind of draw the figure again for you, it looks like this, right? And so we have surface 1 and surface 3. They're kind of, sitting there and looking at each other, right? And so this is another case where we have to look this up in a table. Okay. And so if you look at 13.1 and you try to find an entry in that table that looks like this, what you see is that this falls into the category of parallel plates connected with their midlines. Okay.
Professor?
Yep.
What page is table 13.1 on again?
Oh, I'm not sure because I'm running with an older version of the textbook, and so it should be one of the first tables you encounter in chapter 13. Yeah.
Okay.
It is the one with the curves, correct?
Yes. Yeah.
Oh, man, just making sure.
Mm-hmm. But if I give this to you in the exam, I would give you just the formulas for these view factors. So, just like on the last exam, I don't want you guys flipping through your books. Even if I do have them available for you, but I think spending time flipping through your books is kind of a waste of time during the exam. So, so for the exam's sake, I'm showing you where you would find it in the book, but for the final exam, I would just give you these formulas. Yeah. All right. And so if you look in table 13.1, under that category, what you get is F13 is equal to L1 plus L3 squared plus 4, all raised to the 1/2 power minus, minus L3 minus L1 squared plus 4, all raised to the 1/2 power. Okay. And then you divide all this by 2 times L1. Okay. All right. And so we have everything here. In this case, L1 and L3 are the same. Okay. Okay. And then what you get for F13 here is equal to 0.82. Okay. Right. And now that we have F13, we can go ahead and compute the radiation heat exchange between 1 and 3 using the exact same formulas before. Right? So we have Q13. This is equal to F13 A1 times sigma T1 to the 4th minus T3 to the 4th. Okay. And so you plug in all the numbers for this and you get a heat transfer value of 20,234.2 watts. Okay. All right. Any questions on this part of the example? Okay. All right, and so let's do the last part. And so the last part is between surface 1 and the surroundings.
Professor?
Yep.
Do you think you can go back just like a couple seconds?
Oh, sure. Mm-hmm.
Thank you.
Yep. Mm-hmm. so let me draw the image here, okay? And so we have surface 1 that was on the right side of our domain. And then the surroundings was kind of like this opening right here, okay? Right. And so we need to find the view factor between surface 1 and the surroundings. And so I'll call that infinity, F1 infinity, because I'll call the surroundings, infinity, okay? All right, and so we can find this view factor a couple different ways, okay? And so one way that we can find this is, if we assume that the opening to the surroundings here is that if we assume that this is just another plate, it's not technically a solid plate because it's just empty space, but in terms of radiation, we have the radiation that's crossing that kind of planar opening, okay? And so just for the sake of radiation, we can consider it another plate, okay? And if that's the case, then we have the exact same situation as the first part of this problem, okay? And so in that case, we can just repeat the same work that we did from before because this opening is the exact same size as plate number 2, right? And so if we use the formula for a perpendicular plate with a common edge, then we can get the same view factor. And so we'll get its, 0.09. Right? And so that's one way you can do it, right? Another way that you can do it is you can use the summation rule. Because remember, whenever you have an enclosed space, we have to have the rule where all the view factors coming from a surface have to add up to 1. And so that's exactly what we have here because we have surface 1, surface 2, surface 3, okay? And if we kind of draw just a dotted line for these surroundings, okay? Just assuming that this is all an enclosure, then we have an enclosed space, right? And so what this basically tells you is that F12 plus F13 plus F1 infinity, okay? This has to equal to 1, right? And so you can use this to solve for F1 infinity, right? So F1 infinity is equal to 1 minus F12 minus F13, okay? And if you plug in for F12 and F13 that we got from the previous parts, what you get is 0.09, right? And so either way works. And so, either whichever one you think is faster and more convenient. Okay, but I wanted to show you both ways because, we've already gone through the trouble to compute F12 and F13. You can, in those cases, you can just use the summation rule for that. Okay. All right. And so if you, now that we know the view factor, we can go ahead and plug that in. And so Q1 infinity, or the heat transfer from between surface 1 and the surroundings, is equal to F1 infinity A1 sigma times T1 to the 4th minus T infinity to the 4th. Okay, and so you plug in all the numbers for this, and what you get is 30.83 watts.
Professor, may I ask you a question?
Sure. Mm-hmm.
For the summation rule, is there like a condition, like it has to be certain things, or it doesn't matter?
Yeah. So in order to use a summation rule, like you have to form an enclosed space, and so there has to be kind of nowhere. So basically, any radiation that comes off surface 1 has to hit all the surfaces that you've accounted for.
Okay.
And so in this case, we kind of had to draw a phantom surface because, technically there's no surface there up top. But, if we imagine kind of a plane that goes in between surfaces 1 and 3 here, then what we have here is that, any radiation that comes off surface 1, it has to hit one of these 3 planes, right? It's either going to hit surface 2, or it's going to hit surface 3, or it's going to cross that imaginary plane of the infinity plane, right? And so in that case, you have a kind of an enclosed space that you've created, and then from there you can use the summation rule.
All right. And the first part where you made the assumption, is that just like if you want to make it go quick instead of trying to find using the summation rule?
Yeah. So and so you can do either way in this case. And so if you kind of draw that imaginary plane, in this case, it's exactly the same as like another perpendicular plate. And so you can use basically the same formula as F12, which gives you the same answer.
So I guess the assumption part would not work if, let's say, for the imaginary infinity, let's say there's like another plate that goes halfway, like, and so at least like a half of a opening.
So you have something like, say, something like this, maybe, right?
Yeah, something like that, where like so then you have to use the summation rule to get your F now instead of using the assumption.
You can still use this this formula. It's just that the length of this opening would be half. So if you go back to our formula for surface 1, 2, you can see that two of the things that you put in the formula are the lengths of these two surfaces. And so if you had that half opening, you would just plug in half of L2 in for L2. Yeah. You can use the same formula.
All right. Thank you.
Yep. All right. Any other questions on this example here? All right. And so that's kind of the basics of radiation exchange. And so it's the key to these types of problems is finding that view factor. And then once you find one view factor, 2 view factors, then the rest of the problem can be kind of solved from there. Okay. All right. And so now we're going to take this to the next level. And so instead of radiation exchange between black bodies, what we're going to do is we're going to have more realistic radiation exchange. Okay. And in particular, we call this gray body radiation exchange. Right. All right. And so that last example and kind of all the analysis that we've been doing up to this point is we assume that our surfaces are black bodies. Okay. And if you remember, what this basically means is that its emissivity is 1, okay? And so it's a perfect emitter, okay? And also its absorptivity is 1, okay? And this last part here is key because what this basically tells you that any radiation that hits onto a black body, it's going to be absorbed. Real surfaces aren't like this. And so, real surfaces, whenever, radiation hits it, a lot of it can be absorbed, but a lot of it can also be reflected and it can also be transmitted, okay? And so for this, just for simplicity, we're only going to consider reflection, okay? Okay. And so if a radiation wave reflects off a surface, then that one's not going to be absorbed. Okay. And so we need to account for this whenever we're doing radiation exchange between real surfaces. Okay. All right. And so let me also draw this red one here. Okay. And so this red arrow will denote emission. Okay. And so let me define a new term called radiosity. Okay. And so radiosity is a you can think of it as a as what we call all of the radiation that comes off a surface. Okay. And once you start taking reflection into account, the radiosity is basically going to be a sum of the emission and the reflection. Okay. All right, and so usually we give radiosity the symbol J. Okay. Don't ask me why, I have no idea, right? And so radiosity J is equal to E, which is our emission, plus the reflection. And so reflection is usually given by the reflection coefficient rho, or the reflectivity, multiplied by G, where G is the amount of radiation that hits onto the surface, okay? All right. And so, now that we're considering, realistic surfaces like this, we need to consider the amount that's reflected as well, okay? And so instead of talking just purely about emission, we need to talk about reflection as well, okay? All right, so let me actually go ahead and label this, okay? And so this row right here, this is the reflectivity. It's a lot of terms and it's a lot of symbols, I know, but reflectivity, remember, you can think of that as the fraction of radiation waves that reflects off of a surface. Okay, so so reflectivity is some number between 0 and 1. Okay, and G is our irradiation. That's all of the radiation that hits onto a surface. Okay. All right. So any questions on this so far? Okay. All right, and so I'll give you fair warning, and I wish it didn't. This topic didn't have to come at the end, but things are going to get a little bit hairy, and so things are going to get a little bit complicated. And so to kind of make things a little bit simpler and to make things a little visual, let's bring back an old friend of ours from the beginning of the class, which is the thermal resistor. Okay, and so what I'm going to show you next is how we can formulate radiation problems with thermal resistors. Okay. But instead of having the conduction resistance from before, we're going to introduce these ideas of radiation resistance. All right. And so just to kind of get us started, let's kind of remind ourselves what we meant by conduction resistance. Right? And so this is just a reminder or refresher. All right, and so for conduction resistance, we had a situation that looks like this. Okay? So let's say that we have a chunk of material, okay? And it has a thermal conductivity K. We'll say the length is L, okay? On one side, we'll say that the temperature is T1. On the other side, the temperature is T2, okay? And so to form a thermal circuit between this, what we can say is one side we can make one node T1, and make the other node T2. Right? And we'll draw a resistor in between, okay? And what we say is that the resistor is equal to the length of the material divided by the thermal conductivity times A, okay? And then from this circuit, what we can do is we can say that the heat transfer between the two, okay, between the two surfaces is equal to T1 minus T2 divided by R, Okay. And so in other words, we just take the difference in temperature and we divide it by the thermal resistance in between them. Okay. Right. And so that's how we use resistors back in conduction. Okay. I'm going to tell you that, we can use this exact same concept for radiation with a little bit of a twist. Okay. Right. So let's say that we have two surfaces here, and they're radiating on each other. Okay. And so we can say that they're both the surfaces are held at different temperatures. And what we found from the from the previous example with the rectangular furnace is that the heat transfer or the heat exchange between them is equal to A1 F12 times sigma times T1 to the fourth minus T2 to the fourth. Okay. And so what I'm going to tell you is that, from this formula right here, we can draw kind of an analogous situation with our conduction resistance. And then from there, we'll be able to derive a value for the radiation resistance. Okay. Okay. So any questions on this so far? All right. Okay. And so for that radiation problem, let me go ahead and write the formula again. Okay. And so the formula is A1 F12 times sigma T1 to the fourth minus T2 to the fourth. Okay. What if we made a circuit that looked like this? Okay. Where on one side of the circuit we have sigma T1 to the fourth, and the other side we have sigma T2 to the fourth. Okay. And then in the middle right here, we have our resistance. But instead of having conduction resistance, let's define this resistance according to the view factor. Okay. Right. And so if we define that resistance to be 1 over A1 times F12, okay, or another way we can do this is, since we have the reciprocal relationship, we can do A2 times F21. Okay, both of these work. Okay. What we can do is we can find the Q from the circuit. Where, just like we did with convection, we're going to take a difference in between the nodal values. Okay. And so the nodal value is going to be sigma T1 to the fourth minus the other nodal value, which is sigma T2 to the fourth. Okay. And we're going to divide all of that by the resistance. Okay. And so if we plug in for the resistance, what we get is, let me go ahead and factor out sigma from this, okay? Right, and so up top we have sigma T1 to the fourth minus T2 to the fourth, okay? And the resistance that we have here is 1 over A1 F12, okay? And so if we plug that in, or we kind of simplify this a bit, what we get is A1 F12 sigma times T1 to the fourth minus T2 to the fourth. And so this is exactly the same equation that we have up top, right? And so, now that we've made this connection, we can start to think about radiation problems in terms of, thermal circuits, thermal resistances. It's just now that, we have to make some slight modifications for radiation, okay? And so instead of having just the temperatures at the nodes instead we're going to have sigma times, T temperature to the fourth. And our resistances in this case are going to be determined by the areas and the view factors. Okay. So any questions on this so far? All right. And so this is nice because now this kind of gives us a visual way to kind of see these kind of radiation exchange problems. Okay. And so as an example, let's draw the thermal circuit from the previous example. Okay. And so let's say that we have a 4-surface system, okay? Okay. So you have surface 1, surface 2, surface 3, and surface infinity, okay? And so let's go ahead and draw the radiation thermal circuit for this, okay? And so I'm going to take each of our surfaces here and replace them with a node, okay? Right? And at each of the nodes, I'm going to draw the nodal values, right? And so for this one, we have sigma T1 to the 4th. On the bottom, we have sigma T2 to the 4th. Okay, for the left surface, we have sigma T3 to the 4th. And for the top one, we have sigma T infinity to the 4th, okay? All right, and so to recreate the last example that we did, remember in the last example, we computed the heat transfer or the heat exchange between surface 1 and all the other surfaces, okay? And so let's go ahead and draw a resistor that goes from surface 1 to each of the different surfaces, okay? And so first we did 1 to 2, okay? But R12 here is A1, F12 to the -1, okay? Next we had the resistance between 1 and 3. Okay. And so we have R13, this is equal to A1, F13, raised to the -1, right? And then we had F1 infinity, right? And so we have R1 infinity, this is equal to F or A1 F1 infinity raised to the -1, okay? All right, and so that's the, at least considering everything that's coming from surface 1, going to each of the different nodes, okay? And so we can use this thermal circuit to get the same expressions that we had before for the radiation exchange between surface 1 and 2, 1 and 3, and 1 and infinity, okay? All right, and then to compute all these resistances, you would have to know the view factors, and you would either look those up in a table, or you would find them through the view factor rules. Okay. All right. And so you can see it's getting a little bit messy already. But what if I told you that this circuit right now is still incomplete, right? Because right now we have the radiation exchange between surface 1 and all the other surfaces, but all those other surfaces can also radiate on each other as well, right? And so let's draw this resistor right here between surface 2 and 3. Okay. And so there we have R23, and then the formula for that will be A2, F23, raised to the -1, okay? We also have the radiation exchange between surface 1 and infinity, okay? Right, and so that's gonna be R3 infinity, okay? And then we have the radiation exchange between surfaces 2 and infinity as well, right? And so we have, okay, I drew this little kind of bump here to say that the circuits don't cross, right? Right, and so we have R2 infinity, right? Right, and I think that's all of them. Yes, that's all of them, right? Okay. And so you can see here we have a mess of resistors, okay? And so, these systems can get pretty messy in a hurry, but actually, believe it or not, drawing out the circuit like this really helps because, when you have a complicated system, and later on, you'll see once we start taking gray surfaces into account, having a visual representation of these systems is really going to help you go a long way. Okay. All right, and so I'm not going to make you solve this here, but I just wanted to show you how you take a radiation situation and draw its equivalent thermal circuit. Okay. All right. So any questions on this? All right. Okay, so that's black body, and so that's thermal circuits for radiation. Okay, but all we did so far for that one is we just kind of repeated the same black body radiation exchange, but with circuits. Okay, but the whole title of this section was gray body radiation exchange. Okay, and so now the question is, how do we modify these circuits in order to consider realistic surfaces? Okay. All right, and so we're going to modify our circuits. Okay. And the analogy that I want to draw for you guys, connecting it back to our previous ideas, is I want you guys to think about contact resistance. Because basically what's going to happen is, when we have a surface where emissivity is not equal to 1, that's going to add some additional resistance to our radiation circuit. Okay. Okay. All right, and so let's draw the situation. Okay. Okay, and so let's define these two surfaces, and so we'll call this surface 1. We'll call this surface 2. Okay. Normally, if both of these surfaces were black bodies, the only thing that's impeding the radiation exchange between black bodies is the view factors. Okay. Okay. And so we have an initial R12 here, and this is going to be the same as before. So this is going to be just A1, F12 raised to the -1 power. And so we're just going to convert it. Okay. But for real surfaces, we have an additional impediment to radiation heat transfer that comes from the surface itself. Okay. Right. And so let's say that for surface 1, what we have is epsilon not equal to 1. We have the absorptivity not equal to 1, and the reflectivity is greater than 0. Okay. And so here on surface 1, we have a real surface. Okay. Okay. And so we have an additional resistance from surface 1 right here. Okay. And so we'll call this just simply R1. Okay. And I'm not going to derive these formulas here, but these formulas were under the assumption that the surfaces were gray. Okay. Okay. And so we're going to have an additional resistance that comes from just surface 1, which is equal to 1 minus epsilon 1 divided by epsilon 1 over A. Okay. And then we're going to have the same thing for surface 2. Right? And so surface 2, if that one's a real surface, right, where epsilon does not equal to 1, absorptivity does not equal to 1, and the reflectivity is greater than 0. Okay. What we have from this is also R2 is equal to 1 minus epsilon 2 divided by epsilon 2 A2. Okay. And so these surface treatments, or these the surface properties, are going to add some additional resistance to our circuit. Okay. And so from that, instead of just having one resistor in between surfaces 1 and 2, now we're going to have 3. Okay. We gain 2 additional ones from the from the 2 surface properties. Okay. All right. And so on the next page, I'll show you kind of this 3 resistor system. And most importantly, I'll show you how to label each of the different nodes in this circuit. Okay. Okay. So any questions on this? Okay. And so let's draw our new circuit that accounts for these 2 new resistances here. Okay.
Wait, Professor, can you go back really quickly?
Sure. Mm-hmm.
Like 2 seconds. Okay, you're good. Sorry, thank you.
Yep. Mm-hmm. Right. And so the new thermal circuit looks like this, right? And so on the ends, we still have sigma T1 to the 4th and sigma T2 to the 4th, okay? But instead of just having 1 resistor in between them, now we're going to have 3. Okay. All right, and these 3 resistances are given by the following. And so this one here is R1. This one here is R2, okay? Where R1, remember, is accounted for by the emissivities. Okay, and R2 here is 1 minus epsilon 2 divided by A2 epsilon 2, okay? And then this resistor in the middle here, this is just our normal exchange resistance, okay? So R12 here is A1 F12 raised to the minus 1 power, okay? And so now if we want to compute the total, heat, radiation and heat exchange between these 2 surfaces, we have to account for these extra resistances here, okay? All right. Right, and so if you have just a serial circuit like this, that's all that you would need, okay? But later on, we're going to start to see some really complicated circuits, and so we need to define a couple more things here, okay? Okay, and so after R1 and after R2, I'm going to define those nodal values there to be J1 and J2, right? And if you remember from earlier in this lecture today, J1 and J2 are the radiosities. They're the radiosities for surface 1 and surface 2, okay? Right. And remember what radiosities are. So remember, radiosities are a sum of all the radiation that the surface emits and all the radiation that the surface reflects, okay? So now that we have kind of realistic surfaces, we have to account for that reflection in our calculations. Okay. All right. And so there's a few ways that you can compute the radiation exchange here, right? And so one way you can do it is you can go from the 2 endpoints. Okay. So you can say that Q12 is equal to sigma T1 to the 4th minus sigma T2 to the 4th. Okay. Divided by the sum of all the resistances, and so it's R1 plus R12 plus R2, okay? And so that's one way that you can compute the heat transfer, okay? Another way that you can compute the heat transfer is you take the difference of the radiosities. Okay. And so we can do J1 minus J2, and this is divided by just the resistance in between them, which is just R12. Okay. Or what you can do is you can just do basically any combination of nodes that you can do in between here. You know, later on, you know, next we're going to do an example, but you know, one other thing that's going to be useful for you guys is to do what's called a, you know, we're going to apply one of our circuit laws to this, right? And so, you know, one thing that we're going to have to do, probably not for this next example, but probably for the last example that we'll do on Monday, is we're going to have to sum up all of the radiation heat transfer that comes in at a node. Okay. Right. And then I'll show you how to do that on the next page. Then we're going to do an example. Okay. And then from there, you know, we'll wrap up for today. Okay. So any questions on this so far? Okay. And so let me show you how to sum up the radiation heat transfer at a node. And so this is very reminiscent of circuit laws, if you kind of remember that. Right? All right, so let me just draw kind of just a segment of the circuit, just to show you, you know, just to illustrate this point. Okay. Right, and so this is just kind of the left side of the circuit. Right. And so let's say that, you know, what we want to do is we want to sum up all of the radiations that go into J1. Okay. All right. And so what I mean by that is, you know, we have to consider all the heat transfer that's coming into this node and then all the heat transfer that's going out. Okay. Okay. And so coming into this node, let's say that, you know, we have heat transfer coming in from here, right? And so we have heat transfer that's coming in from the left. Okay. And then going out of this node, let's say that we have heat transfer going this way, right? From J1 over to R12. Right? Well, I guess we need J2 here for that. Okay, and so so when I say to sum up all of the radiation heat transfer going into and out of the node, what I mean is this, right? And so on one side of the equation, you're going to have all the heat transfer coming in, and on the other side of the equation, you're going to have all the heat transfer going out. Okay. All right, and so coming into this node, we only have just one contribution, and that's going to be from sigma T1. Okay, and so the heat transfer coming in is going to be sigma 1 T1. To the fourth minus J1, okay, all divided by R1, right? And this is going to be equal to all the heat transfer going out, right? And so the heat transfer going out is going to be J1 minus J2 divided by R12, okay? Right. And of course, you know, you can plug in numbers for this in order to, you know, in order to get an equation from this, right? And so the reason I'm showing you this is that, you know, the way that these radiation problems occur is that usually the thing that's going to be unknown in these problems are going to be the radiosities. Okay. Okay. And so a big part of these radiation exchange problems is to solve for those radiosities. Okay. The issue with this is that, you know, it's difficult to solve for the radiosities kind of outright, right? And what I mean by that is, for a relatively complex system, you might have 2 or 3 or 4 different unknown radiosities, depending on how many surfaces there are, right? In order to solve for these radiosities, you know, we have to solve for all of them simultaneously using a system of linear equations. And a system of algebraic equations is just, just algebraic equations that have J1, J2, or however many J's that you have, right? And the amount of equations that you need depend on how many unknown J's there are, right? And so if you have 2 unknown J's, then you're going to need to have 2 equations, okay? And the way that you obtain these equations is to sum up all the radiation that goes into and out of a node, okay? Right? And so depending on how many unknown radiosities there are, you're going to have to come up with that many different linear equations, okay? Right, and so I'll show you how to do that on the next example, but I just want to give you kind of a heads up of where we're going, and to just kind of explain what I do in a certain step when I sum up these radiations. Okay. Okay. So any questions on this before we do the example? Okay. All right, and so let's go ahead and redo an example that we did earlier. And so let's do our concentric spheres, except this time I'm going to put numbers on this so we can actually solve. So this can be radiation exchange between spheres. Okay. So let's say that we have a big sphere and a little baby sphere, right? And then we'll call the inner sphere, we'll call that surface 1, and we'll call the outer sphere surface 2. Okay? And so the properties of the inner sphere, let's say that we have T1 is equal to 600 Kelvin. Okay? We'll say that epsilon 1 is going to be 0.8. Okay? And then D1, the diameter of the inner sphere, is going to be 10 centimeters. And then surface 2, we'll say surface 2 is a little bit cooler, so we'll say surface 2 is at 400 Kelvin. Okay. Epsilon 2 is equal to 0.7. Okay. And then D2, we'll say is 20 centimeters. Okay. All right. And so let's compute the first, let's draw the thermal circuit for the situation. Right? And then from that thermal circuit, we're going to compute the radiosities, and we're going to compute the radiation exchange between them. Okay. All right, so let's start with the thermal circuit. And so thermal circuit, we have just a 2-surface system. And so for a 2-surface system, we can draw the exact same circuit that we drew before. And so for 2 surfaces, we have 3 resistances, right? And so we have one resistance for each surface, and then the exchange resistance in between them. Right? Right, and so our circuit looks like this, okay? And so we have our 3 resistances. So we have R1 is equal to 1 minus epsilon 1 over epsilon 1 A1. Then we have the exchange resistance. That's equal to 1 over A1 times F12, which is the view factor from surface 1 to surface 2, okay? Then we have the surface resistance for surface 2, which is 1 minus epsilon 2 divided by epsilon 2 A2, okay? And then we also have our radiosities, okay? And so radiosities are going to be J1 and J2, right? And in the next step of the problem, we're going to solve for these radiosities using this thermal circuit, okay? All right. So any questions on this example so far? Okay. All right, and so let's go ahead and start solving for the radiosities. And so for this particular problem, we have two unknown radiosities. Okay. And since we have two unknown radiosities, we're going to need to have two unknowns. Okay. Or two equations, sorry. All right. And then the two equations that we're going to get are going to be, we're going to sum up all of the radiation that comes into the J1 node, and then we're going to sum up all the radiations that goes from the J2 node. Okay. All right, and so let's do the J1 node first, okay? And so the J1 node is this guy right here, okay? And so we need to consider all the radiation coming in and going out, okay? Right. And so all the radiation coming in, we know is coming in from this side right here, okay? And all the radiation going out is going to go over to J2, okay? All right, and so we're going to do the same thing we did before. And so on one side of the equation, we're going to do in. And on the other side of the equation, we're going to do out, okay? All right, and so coming into J1, what we have is sigma 1 T1 to the fourth minus J1 divided by R1, okay? Next, we have everything going out. And going out, we have J1 minus J2 divided by R12, okay? All right. And so everything here we can compute, actually. And so except for the J's, okay? Because we know that R1 right here is 1 minus epsilon 1 divided by epsilon 1 A1. Okay. And R12 here is 1 divided by F12 A1. Okay. All right. And so let's go ahead and compute A1 and F12 here because those are still unknowns. Okay. Because we know epsilon 1 is given in the problem as 0.8, I believe. Okay. And so the only thing we need here is the area. And so the area here is going to be the surface area of the sphere. Okay. And so the surface area of the sphere is going to be, let's say this is pi. Oh, I'm sorry. Oh, so these are actually just circles here. Okay, yeah. So these are just circles, not spheres, and so we'll just consider them just circles, and then we'll consider them to be cylinders down the length, right? And so not sphere here; these are cylinders. Just to be kind of consistent with the note. So I apologize for that. So these are cylinders and not spheres. Okay? And the length of the cylinder into the page we'll consider it to be 1 meter. Okay, and so the area of the inner cylinder here is going to be pi d1 times L. Okay, and then the view factor from the inner sphere to the outer one, or the inner cylinder to the outer one, in this case is just going to be 1. Okay, and then we solved this before just by inspection. Because what we can see from here is that, because surface 1 here is a convex surface, right? We know that there's no way for it to radiate on itself, right? And so any radiation that comes off surface 1, there's no way for it to touch surface 1 again, okay? And so since we have an enclosed surface right here, everything that leaves surface 1 has to hit surface 2, okay? Right? And so F12 here is going to be 1 just by inspection. All right. And so you plug all this in. Okay. And so you plug all this in and simplify. What you get from this is the following equation. Right? And so you get, on one side of the equation, you have 9,234.17. Okay. And this is equal to 1.57 J1 minus 0.314 J2. Okay. Right. Okay. And so this is our first equation here for the radiosities, okay? And so you can see here, it's by itself, we're not able to solve for it because, we have J1, which is an unknown, and J2, which is an unknown as well, okay? And so in order to solve for this, we need one more equation that involves J1 and J2, okay? And so for that other equation, we're going to sum up the radiation around the J2 node, okay? Okay, so any questions on this? Okay. All right, and so now let's sum up everything around the J2 node. Okay. And so for J2, let me just draw the J2 node here. Okay. Okay. And so same thing we did before. We're going to do all of the radiation coming in compared to all the radiation coming out and set them equal to each other. Okay. And so coming into this node, we have J1 minus J2 divided by R12. Okay. And then coming out, we're going to have J2 minus sigma T2 to the fourth. Okay. Divided by R2. Okay. All right. And so you plug these two in, plug everything in, and then you're going to get another equation that involves J1 and J2. Okay. And so our second equation is 2128.04 is equal to 1.78 times J2 minus 0.314 J. Okay. And this here gives our second equation. Okay. All right. And so now that we have the equation on the previous page, and then we have this equation here, we can solve for them simultaneously in order to obtain J1 and J2. Okay. Right, and so hopefully you remember your linear algebra because you're going to need it for this one. Okay. All right, and so I think I'll finish this up on the next lecture just because we have about 30 seconds left. And so, are there any final questions before we sign up for today? Okay. All right, so that's all we got time for. So thank you guys for tuning in today. And so I hope you guys have a good weekend, and I'll see you guys on Monday.
Thank you, Professor.
Thanks, guys.
One last thing, Professor, off topic.
Yep. Mm-hmm.
They landed a SN15.
Nice. That's great. Very exciting.
Later, Professor.
Have a nice day.
Thanks, you too.